Okay, so in this video we're going to be looking at section 4.4, dealing with the logistic equation. And the idea of the logistic equation is to try to take the concept of exponential growth and mediate it with the idea that there's some sort of a carrying capacity or some maximum that a population could achieve, and therefore the idea of unbounded exponential growth, as you know, looking like this, is really unrealistic. If there's some capacity that we cannot supersede, then as we approach this capacity, our growth rate is going to slow. It's going to be mediated by that capping. Okay, so as time goes on, our population of, say, a bacteria, it's not going to continually grow unbounded like this. It's going to reach a peak. And the idea is, initially, our growth will be in an exponential form. But as time goes on, the fact that there's a carrying capacity or a peak to our population that we cannot pass is going to be come into play and cause this exponential growth to slow down and turn into a different type of growth, as we're going to see. Okay, so we are again considering bounded growth, bounded by a maximum carrying capacity to our population. And we're going to denote this maximum capacity with the letter capital K. Now, let's give the definition of the logistic differential equation. Again, we're letting K represent the carrying capacity. For an organism. And we let R be the growth rate for the population. Which is measured by P of T. Okay? We let P naught be the initial population. At time T equals 0. Then the logistic differential equation is the following. The change in population with respect to time, dp dt, is equal to that rate of growth that we talked about times the population times 1 minus P naught minus P over K. Okay? And so let's see what this is actually saying. When the population is small, of course, P over the carrying capacity is close to 0. Now imagine that, if P over the carrying capacity is close to 0, okay, that's this part right here. If that's close to 0, then all you have is 1 minus 0 is 1 times RP, which says that the change in population with respect to time is the growth rate times the population. That is unbounded growth. The solution to that is the natural exponential function. Okay? But when P approaches the carrying capacity of the population, then P over K is approximately 1, which means you have here 1 minus 1. And this entire component then is approaching 0. Rp times 0 is 0, which is saying then as the population gets close to the carrying capacity, dp dt is approximately 0, meaning the change in the population with respect to time is going to 0. Okay? All right. Now, let's see how we would solve this. We do this by separating variables. Okay. The p times the 1 minus p over k, that part comes over to the denominator. The r stays up here and the dt joins it. So what we get is 1 over p times 1 minus p over k equals r dt. Now, if we want to clean up this complex fraction here, we would do so by multiplying the top and the bottom by a k. That gives us a k in the top. The k in here, I can either choose to multiply by the p, or I can choose to multiply by this 1 minus p over k. And of course, this is the term I want to multiply that k by. So bringing that k inside the parentheses, in other words, you get k minus p. And I forgot the dp here. There we go, dt. The dp is still there on the left. Okay. All right. Now, think about how we would separate, or how we would integrate this on both sides. This is simply a partial fraction decomposition problem here. So I have to figure out how this decomposes. K for p times k minus p is going to be a constant over p plus another constant over k minus p. And as we solve this, as it turns out, both a and b turn out to be 1. And so there's the way we decompose the left-hand side. dp, there we go. Now, integrating the left-hand side, you get the natural log of the absolute value of p minus the natural log of the absolute value of k minus p by a simple u substitution. U is k minus p, du is negative 1. There's where the negative comes from. And integrating on the right-hand side, we get RT plus a constant of integration. Now, by properties of logarithms, these two on the left go together. And I get this expression. Now, I can solve that for p. It's a little bit of work, but I can solve that for p. What I'm going to do is first get rid of the natural log. And of course, we do that by using the natural exponential composed on both sides of the equation. I'm sorry, I missed that little piece here. Okay? We did the partial fraction decomposition. We integrated. We combined these two logs together into a single logarithm. And now I want to get rid of this logarithm by using the natural exponential on both sides of the equation. So, let's go ahead and get rid of that logarithm. What I'm going to do is exponentiate both sides. P, k minus p is e to the rt plus c. And since the natural exponential is always positive, I don't need to write the absolute value anymore. Now, just as before, e to the c becomes a constant. We can call that c e to the rt. Okay? All right. Now, in order to solve for p, what I'm going to have to do is multiply both sides by this denominator, putting it up here, and then combine my p's together. So the k multiplies the ce to the rt. The minus p multiplies the ce to the rt. Okay. Now put these p's together on the left. P plus p c e to the rt is k c e to the RT, factor out the p, and then divide by what's in the parentheses to get p. And there we go. Okay. Now let's apply the initial condition here. Okay, that at time 0 the population is p naught, and see what that gives us. P naught is kc e to the 0, 1 plus c e to the 0, so that's kc over 1 plus c. That's our p naught in this problem, or yes, our p naught value. Okay. Okay. If I solve for c now, in terms of that p naught, the way I would do it is, again, multiply both sides by 1 plus c. So p naught times 1 plus p naught times c is kc. I want to get the c's together. So let's subtract the p naught c from both sides. Factor out the c. And then divide. And there is the constant in this problem. So now we can go back up here to this form, and we can plug in what that constant is in terms of p naught, the initial population, and k, the carrying capacity. And we have this form, which is again a complex fraction. So let's go ahead and multiply k minus p naught on the top and on the bottom to clear these denominators. So on the top, what we'll be left with is the p naught and the k times e to the RT. In the bottom, the k minus p naught will multiply this 1, forming a term here, plus here the k minus p naught will cancel, leaving p naught e to the RT. And so there's our final form that we can consider as the solution to the logistic equation. Okay. Now, quite a messy form that we end up with. All right. Now, let's take a look at some of these exercises that we have to consider in this section and see what it is we're supposed to be able to do. Let's start with problem number 170. Okay, we don't have to solve an equation here. We're just going back to the ideas of the equilibrium points and the direction field. So in problem 170, you're given the differential equation. P prime is Cp minus p squared. And you're asked to draw the direction field and find the stability for this differential equation, given that c is -3. So that simply means we're going to plug in a -3 for the c. P prime is -3p minus p squared. Okay? And then we're going to figure out what the direction field looks like for this. Now, finding the equilibrium of this is a good way to start. And the way we find the equilibrium is we say, when is p prime equal to 0? When is our rate of change in p going to be 0? So you set -3p minus p squared equal to 0, and you solve this for p. And we do that, of course, by factoring out a p. And so we get p is 0 from here, and from here you get p is -3. -3 minus a -3 is 0. And that allows us to understand that when p is 0 or when p is -3, on the direction field, there's -3 for the p value, and there's 0 for the p value. Those are the two equilibrium. Okay? Now, with this broken down, we can consider these regions. Here's the region where p is positive. If p is positive, and again, remember, p prime, if we write this in its factored form, it's a little easier to see. P prime is p times negative 3 minus p. If p is positive, then this is positive. Negative 3 minus a positive is going to be negative. A positive times a negative is negative. So the rate of change in p is going to be negative. And that means your direction field is going to be going always downward when p is above 0. Now, when p is between 0 and negative 3, let's see what the direction field would look like. Well, if p is between 0 and negative 3, p is certainly negative, so that term's negative. Negative 3 minus something between 0 and negative 3 is still going to be negative. For example, if that was a minus a negative 2, that would be negative 3 plus 2 is a negative 1. A negative times a negative is going to give you a positive rate of change in p. So on this interval, between 0 and negative 3 for the value of p, our direction field is upward. And what that tells me is that this equilibrium point here is stable. If we're here or here, we're going to tend toward p equals 0. Finally, what about when p is less than negative 3? Suppose p is negative 4, for example. Well, a negative 4 would make this negative. A negative 4 here, this would be negative 3 plus 4 would be a positive. And a negative times a positive is negative. So the rate of change in p is negative on this part of the diagram. And so what that tells you about this equilibrium is that you're going to tend away from it. If you perturb slightly here, you're going to shoot up. If you perturb slightly here, you're going to shoot down. So this is an unstable equilibrium. Okay, and there's our analysis of problem 170. Okay. Now let's take a look at problem 174. In 174, we read that a population of frogs in a pond has a growth rate of 5%. If the initial population is 1,000 frogs and the carrying capacity is 6,000, what's the population of frogs at any given time? So they told us the growth rate is 5%, 0.05. They told us that the initial population of frogs was 1,000. P naught is 1,000. And they told us the carrying capacity is 6,000 frogs, so K is 6,000. We simply plug this into the logistic equation that we have. Here's again the logistic equation that we're working with. So the population is the P naught, 1,000, times the carrying capacity, 6,000, times e to the r, 0.05 t, divided by k minus P naught, 6,000 minus 1,000, plus the P naught, 1,000, e to the r, 0.05 t. And that's what our solution looks like. Now let's clean this up a little bit. We have 1,000 times 6,000 e to the 0.05 t up top, and in the bottom 6,000 minus 1,000 is 5,000, plus 1,000 e to the 0.05 t. If I simply divide the top and the bottom by 1,000, that'll become a 5, that'll become a 1, and that 1,000 will go away, and we're left with this simpler form to work with. 6,000 e to the 0.05 t over 5 plus e to the 0.05 t. And that's a simpler, of course, to look at than all those big numbers in that problem. Okay. All right, so there's our solution to problem 174. Now let's take a look at problem 188, all the way up to 188. In 188, they tell us that we should consider a modified version of this, and they say it's more likely that the amount of fishing is governed by the current number of fish present. So instead of a constant number of fish being caught, The rate is proportional to the current number of fish present with proportionality constant k. And they give us a differential equation then to consider. Okay, so obviously they're talking about a problem that they've looked at in some previous exercises as well. But what matters to us is that they're giving us this differential equation. P prime is 0.4p times 1 minus p over 10,000 minus k times p. Okay? And they're telling us in problem 188 that we should use the value of k to be 0.05, and we should have an initial condition of 5,000 fish. P naught is 5,000. So that means that our differential equation looks like this. For P prime, I'm going to write dp dt so I can get explicitly that's with respect to time. Makes it a little clearer to understand, I think, when you put in the differentials. 1 minus p over 10,000 minus the 0.05 for the k times p. Okay? Now, if I multiply out this right-hand side, 0.4p times 1, and then the 0.4p times the minus p over 10,000, well, that's a minus 0.4p squared over 10,000. And then there's this minus 0.05p. I can now combine these two terms together. Let's see. Too many minuses. There we go. Okay. And now if I choose, I can write this with a common denominator of 10,000. 0.35 times 10,000 is 3,500. And I have that. Okay? All right. Now, remember that's dp dt in the differential equation. And now I can separate the variables. This 3,500p minus 0.4p squared is going to come to the denominator. And this 1 over 10,000 will stay over here. The dt will come up and join it. And we have separated. And now that means I can integrate both sides to get my answer. Now, when I look at integrating this left-hand side, I realize that this is a rational function, and I can factor out a p. And so now I have to do the decomposition of this. The 1 over p times 3,500 minus 0.4p is going to decompose into an a over p plus a b over 3,500 minus 0.4p. So working this out, what I get for my values is a is 1 over 3,500, and b is 0.4 over 3,500. So now, carrying out the integration, integrating this constant over p, I get the constant times the natural log of the absolute value of p. And integrating this, since I have a negative on the p, I'm going to get a negative in front, and this is going to be 0.4 over 3,500, the natural log of that 3,500 minus 0.4p that's there. Oh, and the 0.4 cancels with the differential from this, so it's a 1. Sorry. All right. Now on the right hand side, I'm integrating just basically a constant times dt, so that's the constant times t plus c. Now on the left hand side, I can factor out the 1 over 3500, and then the natural log of p minus the natural log of 3500 minus 4p go together. 0.4p. And so I notice if I multiply both sides by 3500, over 10,000 plus just another constant. All right. So where does that get us? Well, certainly I can cancel a couple of zeros here. 35 over 100 for that. And I think we can move on to a new page now, can't we? Let's see. Where are we? The natural log of p over 3500 minus 0.4p is, let's see, 35 over 100. Let's just write that as a decimal, 0.35 t plus the c. All right, now let's get rid of the natural log here. Exponentiate both sides. This e raised to a c is still just a constant as a coefficient, so that's what we have. Okay? All right, now let's solve for that c before we go any further. And we solve for that c by using the fact that the initial population was 5,000, meaning at time 0 the population is 5,000. P naught is 5,000 is what they told us. So plugging in for p 5,000, it's that constant times e to the 0.35 times time 0. All right, now 0.4 times 5,000 is 2,000. 3,500 minus 2,000 is what, 1,500, right? And over here, e to the 0 is 1. So there's your constant c. Cancel. It's 50 over 15. Or if we want to reduce that by dividing by 5 in the top and the bottom, get even simpler. 10/3 is your constant c. All right. So that means we finally have a value of c to plug in to the differential equation up here, and that c is 10/3. All right, now I want to solve this for p. Well, of course, what I have to do is multiply both sides by the denominator. The 3,500 minus 0.4p is going to multiply both sides of this equation. And so that means I'm going to have 10/3 times 3,500, or 35,000 thirds, e to the 0.35t, and then a 10/3 times the 0.4p is going to be a 4/3 p. Okay, 10 times 0.4 is 4, so you get 4/3 for that p. Okay. All right, now let's add 4/3 p to both sides. 1 plus 4/3 is 7/3. Oops, I can't quite do that, can I? Let's see. This 0.4p is still multiplying this e to the 0.35t. Sorry about that. So, I have to factor out the p. And then divide by this. And so finally we get p is 35,000 over 3 e to the 0.35t divided by what's in the parentheses here, 1 plus 4/3 e to the 0.35t. And there's our final solution to this problem. All right, that is the last problem for us to consider in section 4.4, so please go forth and try your homework. Make sure you're able to work the logistic equation, logistic differential equation, which of course involves the process of separation of variables. And partial fraction decomposition often plays a prominent role in doing the separation of the integration of the separated form once you're done. Okay, good luck, and as always, let me know if you have any questions that we can look at together.